Alright, so let's say you're given this ideal dipole here. The question asks you to find the electric field at point R from the dipole. To start, the electric field of a dipole can be found from its electric potential, given by this equation here, where del vector represents the divergence operator, given by this, and then V is the electric potential, also called the scalar potential. In general, we can find the scalar potential of a random 3D volume of charge. If we take a random volume of charge here, we can draw this point. This is going to be our R vector, where we're going to find the scalar potential at this point, and then we can draw a arbitrary length R prime. This is going to be our contribution at some random point on the volume. This distance here is going to be R minus R prime. We can use the Coase law here, and if you use this general equation for the scalar potential where d tau is the volume element, so it's going to be a small chunk on the volume of charge. PR is going to be our charge density. R minus R prime, this is the distance between our reference point R and the contribution of point R prime to the total electric potential. If we plug in our definition for R minus R prime into the equation and solve, we can find the electric potential for the general case, which is given by this, where the first term is the point charge contribution, and the second term is the dipole moment contribution, where the p vector is equal to the dipole moment. We can note that if q is not equal to 0, the first term dominates. The arbitrary volume is going to behave like a point charge, and if q equals 0, this means that the second term dominates, so the arbitrary volume behaves like an ideal dipole. And then a second note, in general, the total charge can be found using this equation, so it's summing over the charge density over the entire volume, and the dipole moment can be found by summing the charge density over the volume and multiplying it by the distance from the volume. So we can apply this to our example. And so what is our charge density? Charge density is given by this, where this del3 is the canonical delta function in 3D. And we use this because in a general case, to describe a charge, when R is not equal to 0, the charge density is equal to 0. And then when R is equal to 0, this means we're right on top of the charge. The charge density is infinity. If we take the 3D integral over the charge density, we get Q. And so we use this canonical function to describe the charge density over the entire 3D space. That's why we use the canonical delta function here. And so what is the total dipole moment? The dipole moment is given by this equation, and if we plug in the charge density we just found, we can evaluate that the canonical delta functions only yield values at r equals d divided by 2 and r equals negative d divided by 2. These are going to be the two locations of the positive and negative charge. And so if we use this and evaluate the integral, we get the dipole moment equal to q times d. Our general scalar potential function is given by this, and so q is equal to 0 because we know that the total charge is 0 for a dipole. We can plug in the dipole moment we just found and we get this. So this is a scalar potential for an electric dipole, and so we can find the electric field using the equation below. So if we plug in the divergence and the scalar potential, we find the electric field of the dipole is equal to this, where p is the total dipole moment and r is the distance from the dipole. And so we can note that physically an electric field of an ideal dipole looks like this, where the dipole moment travels from the negative charge to the positive charge, and the electric field travels from the positive and loops around to the negative. Always for an ideal dipole, the scalar potential is given by this equation.